The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Thank you. Good morning, good afternoon, and good evening, wherever you are. So welcome to this latest installment of our AI for Climate Science Discovery Series. This week, it's my pleasure to introduce Marlene Kretschmer. Marlene is a junior professor of climate causality at the Leipzig Institute for Meteorology in Germany. She completed her PhD in climate physics at the Potsdam Institute for Climate Impact Research, where she worked to understand the drivers and impacts of stratospheric polar vortex. Following those studies, she worked as a postdoc for a while at the University of Reading, which I think where we met, and she currently co-convenes an EGU session with me on machine learning for climate science. So it's our pleasure to have you here, and looking forward to your talk.
Thank you. I guess I just share my screen.
Yep. When you're ready.
Did it work?
Looks great.
Perfect. Thanks, Duncan. Thanks, everyone. Thanks for inviting me. Yeah, really honored, but also nervous to be included in this great seminar series. And yeah, I'm going to talk about climate causality, which is kind of a broad title. And I gave it the subtitle, Connecting Data and Theory to Understand the Drivers of Regional Weather Extremes. And actually, I just yesterday I watched Stefan Rasp's great talk on the series on Weatherbench 2 and the second revolution of weather prediction. And I'm just showing here a screenshot of his last slide, what he called the big questions. And I highlighted his last 3 bullet points here, which address the use of AI or machine learning for predicting extreme events, also longer timescales such as sub-seasonal, seasonal, and also using AI for climate predictions and projections. And actually, my research focus or my interest is exactly around these 3 aspects. And while I will not give a complete overview of AI on these things, I hope that my talk today will give some insights about challenges and opportunities here. So yeah, thanks, Stefan, for this perfect introduction. And if you didn't watch his talk, please do so. It's really great. Okay, so extreme weather events and climate events are all over the news, unfortunately. So we have increase in droughts and heat waves, wildfires, but there are, of course, other extremes as well: hurricanes, storms, floods, cold waves. In short, extreme events impact people's life. So society, economy, they're all affected by these extreme events. And with climate change, we already have some observed trends in extremes. And this is from the latest IPCC report, a figure which I think is quite compelling, which shows observed trends or observed changes in heat extremes. So this is, kind of a stylized world map, and red means, or shaded areas means that there's an increase in heat extremes. So basically, there's an increase basically almost everywhere. So there's no blue, there's no decrease. And then you have these dots on the different subpanels. And many dots mean there's a lot of, or there's medium or up to high confidence in the human contribution to these trends. And not too surprising, we see that there is there's a lot of confidence in the human contribution and the increase in heat extremes all over the world. When we look at precipitation extremes, this changes. So we still have a lot of green, so increase in heavy precipitation, but now we also have many gray shaded areas. And these are areas where we have either limited data or literature, or there's low agreement on the type of change. And also there are fewer dots, meaning there's less confidence in the human contribution. Or you could also translate this basically, we don't have enough data or understanding of what's going on in these regions. And this is about observed trends, but of course, we're also interested in projections and predictions in the near term and long term of these types of extremes, but there our knowledge is limited. In climate science, we have the lucky situation that we have climate models, so physical climate models, which we can, of course, use and which are very powerful. However, when it comes to regional projection, there are so many challenges in climate models. And this is a figure which I think is quite compelling from a paper which is currently under review, which is led by Tiffany Shaw. This is on regional climate projections on different puzzles and discrepancies in models. And this is just a figure we included where we highlight different regions where there are different documented discrepancies between models and observations regarding historical trends. So basically these areas show different variables where the observed trends are outside the model distribution by state-of-the-art GCMs. And this is, of course, a problem when we think about predictions and long-term projections, because one of the possibilities is that just the models are really missing something, and that when it comes to constrain regional projections, we still have some way to go. So what is known for sure is that we know something about the climate system, that we have sources of predictability on these longer ranges. And this, in a nutshell, is thanks to so-called teleconnections, or the large-scale circulation, which are the source of predictability. And kind of the poster child, or the most prominent case, is so-called El Niño Southern Oscillation, ENSO, which I know most have heard already. This is related to changes in sea surface temperatures in the tropical Pacific. And for example, if you have a pattern like this in this El Niño region, this interacts with the atmosphere and can trigger wave strain in the mid-latitudes. This happens, of course, also in the southern hemisphere, where the Rossby waves interfere, for example, with the jet stream or the tropospheric circulation, and can lead to favorable weather patterns in these regions. For example, to increase precipitation in California. So this is this gives us predictability, and this is not only on the subseasonal case, but also it is also known for longer range predictions and projections, that these depend a lot on these changes in dynamical aspects of the climate system. The challenge is now that it's not only ENSO, but there are different of these drivers and teleconnections. So basically all these slowly moving boundary conditions in the climate system linked to snow cover, soil moisture, sea ice, sea surface temperatures. So we have a range of these different oscillations and teleconnections, and where we like acronyms a lot when it comes to teleconnections. So we have the ENSO, we have the MJO, the QBO, the NAO. O often, not always, but often stands for oscillation. But it's just important to know that they are a range of these different climatic modes, recurrent patterns, which can interfere with the atmosphere, which are source of predictability or so-called windows of opportunity. But at the same time, they all interfere, they're interlinked, operate on different timescales. And it's challenging to basically disentangle the different contributions. So in a nutshell, improved understanding of these teleconnections is really key to reduce uncertainties about near and long-term predictions. But extracting this information from data is usually difficult. We have a limited observation, we have models which are flawed, and we don't really have the tools to combine all this. So when it comes for predictions, interpretability and trustworthiness, of course, also key. So we really need to kind of predict what could happen, but also explain why. And basically to wrap up this motivation or this introduction, I want to just give one example of the stratospheric polar vortex, as Duncan said, what I also did quite a lot of research on. So the polar vortex is a band of these fast-blowing westerly winds in the stratosphere. And I come back to this later in my talk too, which forms in boreal winter. There's also one in the southern hemisphere. And just for mid-latitude boreal weather, we know that the polar vortex is an important driver on sub-seasonal timescales. For example, a weak polar vortex or sudden stratospheric warming, which just also happened this week. This can lead to a weakening or the southward shifted jet stream negative phase of the North Atlantic Oscillation. So it's a well-documented driver, but at the same time, how it interacts with other drivers such as ENSO or the QBO, MJO, this is not well understood. Another challenge, which is kind of typical for these regional climate change or teleconnection affected aspects of the climate system, is that climate model projections are very uncertain. Below you see a plot, of the paper from Capetco et al., where we just submitted the part 2, where you show the different CMIP6 models and their projection of the polar vortex strength. So on the y-axis you have U, so zonal mean wind speeds in the stratosphere. And then you see roughly half of the models have these blue or negative changes, so they predict a weakening of the vortex, whereas the other half predicts a strengthening of the vortex. So we basically don't know what's going to happen. But given that the polar vortex also affects tropospheric circulation, this uncertainty in the projections of the stratosphere, this also causes uncertainties in tropospheric projections. For example, it was shown that depending on how the polar vortex will change in the future, this will also depend on the pace of Mediterranean drying, or also extreme storminess in Europe. And I guess, or this is kind of the point I try to make here, is that this is kind of a typical situation when it comes to these dynamical changes or dynamical drivers, that there are many uncertainties in models and many things we don't understand yet. So in this talk, or maybe my work in general, I'd say I'm interested in these questions in climate science regarding sub-seasonal to seasonal to climate predictions with a focus on teleconnections. I try to combine this with something, or what we so-called causality, which is mostly or more or less overlapping also, or has some overlaps with AI. And partly and also with deep learning nowadays. So in this talk, in this first part of this talk, I have 2 parts. I will first focus on this intersection between climate and causality. I will talk about some older work on using causal reasoning for teleconnection, or for analyzing teleconnections. And in the second part, I will then focus a bit more on this intersection of climate and AI, and talk about recent work on using machine learning for targeted weather regimes. And we'll try to wrap this up, let's say, and commenting on all 3 aspects at the end of my talk. All right, so part 1. I tried to make this a very quick introduction because there was also a very good talk in this AI for Good series by Jakob Rung and Emma Ebert-Uphoff on this. But causal inference, in a nutshell, it's a mathematical framework to formally include causal knowledge in the statistical analysis. It's mainly shaped by work from Julia Pearl. There's this also popular book, The Book of Why, which appeared a few years ago, which I think triggered also a lot of discussions in this direction. And it's basically about quantifying cause effects from data. He introduced this causal hierarchy, which is maybe a key to this causal thinking, where it's important to differentiate between association. So this is what we know, correlation. So we have some conditional probability, y given x. But there's a difference to so-called interventional conditional probability, where we would think that we intervene in the system, and this is done, or this is formalized with the so-called do operator. So this is the conditional probability of y, given that we intervened in x. For us in climate science, it's, I guess, quite intuitive, because that's what we do with climate models. We intervene in the model, we change some settings and see what happens, and this we can then trace back to the cause. There's another layer in this causal hierarchy which relates to counterfactuals, which again, and when it comes to attribution, extreme event attribution, is there's an obvious link, but I will here actually focus on this difference between association and intervention. And to give just one more example, this is of association versus intervention, is then this scatter plot of you have x and y. There's obviously a linear relationship between the two. But if we ask, and we could use x to predict y, we could also use y to predict x, just giving this association we have on this lowest level. But when we ask what happens if we intervene in x, so if we did something like in a climate model, or when we, I don't know, change something by hand in the system, what would happen? And then obviously the answer depends on how x and y are causally related. So whether x causes y, or whether y causes x, or whether there's a common driver z which affects x and y, we cannot tell just based on the data. So this is another important point here. So data doesn't speak for itself. But when it comes to predict the effects of intervention, we have to know the data generating mechanisms. A famous example in this context is the so-called Simpson's paradox. And this is from the causal inference primer from Julia Pearl. So this is an example scatter plot where you have on the x-axis number of doing exercises and y the cholesterol level. And then on the left, you would assume that the more you exercise, the higher the cholesterol, because there's a positive linear relationship. However, when you stratify by age group, this is the plot on the right, you actually see that there's a negative effect for each individual age group. So the question is it now a positive or is it a negative effect? And this is what's the so-called paradox. But actually, when you include or when you assume kind of a data generating model or data generating mechanisms, then it's no longer really a paradox, because you could, for example, assume, or this would make sense to assume, that age affects both the cholesterol level, but also the way you exercise. So children, I guess, run more than older people. And so based on this network, then you can quantify the effect, or the assumed causal effect from exercise of cholesterol. And in this case, you would have to control for age, which is a confounding factor. And so the key point, so that would be the panel on the right from the previous slide. And the key point here being that really the answer depends on a causal model. Just based on data, we cannot derive causal effects. However, if we make assumptions on the mechanisms behind the data, then we can derive causal effects sometimes. And the rules when this is possible is given by causal inference theory. Just quickly, like 3 years ago, we had a paper on this where we introduced this concept in the context of teleconnections, and where I think it makes a lot of sense, because we have some knowledge, we also know these interactions, and at the same time we have time lags, and we have not synoptic timescales, but we are talking about weeks, months, seasons, where we usually talk when we talk about teleconnections, such that we can really ignore some of the coupling effects of the climate system. That's this paper. Apologies. In this paper, we go through different examples from starting on the bottom top left. So we have an example of common drivers with the NAO and precipitation in Denmark and Mediterranean. We discuss how we can quantify direct and indirect pathways in the climate system, such as in the southern hemisphere with ENSO or the jet stream, the polar vortex. We also have an example of more complicated linkages with Arctic mid-latitude linkages, where we have two-way interactions of blocking and sea ice loss. And then we discuss some nonlinear interactions. And importantly, we also include a Jupyter notebook in this paper. The link you can find in the paper, where you can also play with these different examples, where we put the data, and you can hopefully it's a useful resource when it comes to analyzing teleconnections. Just want to make one last point here, which is again this importance of causal reasoning now, and give an example, not with cholesterol and the number of exercise, but actually climate data. And again, this is this example of having the North Atlantic Oscillation as a common driver of precipitation in summer in Denmark and the Mediterranean. The numbers here are just a way to quantify the links using linear regression. There's another example of this so-called mediator or chain, where we have ENSO affecting the position of the jet stream in the North Pacific and affecting precipitation in California. And so in both cases, we have three variables which are correlated. And just from a statistical point of view, both these cases are undistinguishable. So in both cases, we have that two variables, x and y, are correlated, but they are independent conditional on a third variable. In the example of the left, it's Denmark and Mediterranean being correlated but conditional once we control or regress out the effect of the NAO, so the North Atlantic Oscillation. Whereas on the right, we have ENSO and California precipitation being correlated, but being actually independent once we control for the mediator jet. But let's say the how we interpret, or the causal interpretation of these different models really enters through our causal reasoning. So whereas on the left, we would want to control for the NAO, kind of control away this common driver effect, whereas in the example on the right, we don't want to often, when we, let's say, quantify the effect of ENSO on California precipitation, we do not want to control away the effect we're actually interested in measuring. So the point here, just with the example of Simpson's paradox, or in general, is that we need to bring in causal reasoning. But actually, I'm here. I want to talk about an example which is not covered in the paper, which is on the so-called collider effect. And just to quickly recap, we call this such a structure a common driver effect. And we know that if the causal of the data generating mechanism have this kind of structure, and if we condition on this common driver, then we will remove this non-causal association, or this non-causal correlation between x and y. I think that this common effect structure is a bit less known. In this case, we have z as a common effect of x and y. And so x and y are not correlated. But once we control on this, or condition on this common effect, we would actually introduce a non-causal association between x and y. This is maybe not so intuitive, maybe a bit, it's also known in statistics as selection bias. And well, I like this XKCD example. It says in a statistics conference, raise your hand if you're familiar with selection bias. And then, as you can see, it's a term most people know. So I hope you get the idea that it depends on, let's say, which aspects of a data you look at, your answer might depend on this. And again, this is explained in causal inference by the so-called collider structure. An example from, and this is, I think, Nature Communications paper, which I liked, where they discuss different possible collider effects or common effect biases in COVID data. So, for example, they there was found, I don't know, let's say what state of the art research tells us about this, but that there is a correlation between age and having a COVID-19 infection. And one possibility why we see this correlation might not this is causal, but actually that the data where this correlation was found was based on an app, on a COVID app. And then you could argue that both age and also having a COVID-19 infection is a causal driver affects the way whether you use such an app or not. So this is an example, a non-climate example, that age, how two variables are correlated after conditioning or after making a kind of selection on a common effect. And I here want to discuss quickly an example from climate science. Again, so we're talking about the stratosphere and so-called sudden stratospheric warmings. This shows, it's a busy plot, but you can focus on this black line first. So this shows the wind strength in the stratosphere again. So stratospheric winds. And in winter, this is the seasons are on the x-axis. You see that you have these strong westerly winds, so that we have positive wind in the stratosphere. And then the gray shading is just basically the variability. So the black line is the mean strength, and around this is the variability. In red this is one winter from 2008, 2009, where you see you have this I hope maybe you can even see my mouse, where you have this drop in wind speed, this very rapid drop in wind speed, where you actually have negative wind anomaly, negative winds, meaning easterly winds. And these extreme events in the stratosphere, they happen every other year, and they are so-called sudden stratospheric warmings. We care for these SSWs because we know that SPV anomalies, or stratospheric polar vortex anomalies, they affect our weather, the North Atlantic Oscillation, and SSWs are just a very extreme case of these SPV anomalies. So very weak polar vortex is usually kind of the subset we look at are these sudden stratospheric warmings. What happens if we look at SSWs? In this case, this is not observations, but this is using seasonal hindcasts of ECMWF's seasonal forecasting model, CS5. And what we showed is that when you look at early winter SSWs, that they show stronger surface impacts. So you see precipitation in the first row, and temperature anomalies following the 30 days after these sudden stratospheric warmings. But in this case, we differentiate between SSWs which occur in early winter, so December, January, and late winter, February, March. And you hopefully see that the anomalies or the patterns are much more pronounced in early winter. The pattern, by the way, is kind of the expected canonical response to SSW or weak polar vortex. So we have cold air outbreaks in Northern Europe, and we have wettening in the Mediterranean and dry conditions in Northern Europe. But again, early winter SSW show these stronger surface impacts. But what we show is that this is basically a statistical artifact. So if you look at the SSW definition, this includes an absolute threshold. So SSWs are when the zero line is crossed, so when winds turn from westerly to easterly. However, the mean state, so the black line, the black thin line in the middle, so the mean state is stronger in early winter. So this means for an SSW to be classified as one, you need stronger anomalies in early winter than you would need in late winter, where the mean state is weaker. And actually, these stronger anomalies on the x-axis here now plotted for the different winter months, they actually show perfect correlation with the detected tropospheric anomalies for these different cases. So stronger forcings in the stratosphere are also associated with stronger tropospheric effects. So this explains what we found here. And again, we can, let's say, interpret this correlation of these different associations perfectly with the causal inference theory, because SSW is a so-called common effect, which again, causal inference theory tells us that we would expect such an effect. So I expanded this little network I draw here. So in this case, we have, again, our polar vortex anomalies affecting the NAO, and with this particular case of extremes being SSWs. But as I showed, the month also affects if an SSW occurs, just because the mean state is stronger in early winter, and it means stronger anomalies to be fall below this absolute zero line. So SSW is a common effect of both SPV anomaly and the month, making it a common effect. And so if we only look at SSWs, we will find this spurious correlation. And I really like this next figure, which is from this paper, or I forgot to reference it in this slide, from Monin et al., where we show the correlation of SPV anomaly and the NIO anomaly, so stratospheric and tropospheric circulation anomalies for all winter days. And you see a moderate correlation of 0.24. And the different colors, they show again the different winter months. And now if you do the same plot, but only select the SSWs, you really stratified, or basically you really organized the data, and you see that now there is you introduced this correlation between month and SPV anomaly, which was actually not there in the original data. So I do think this is a good example of how a physical definition of SSWs, which makes sense in a physical point of view, which can introduce these statistical artifacts. And we do need this kind of causal reasoning to disentangle or to understand what correlation means, and to basically overcome this mantra of saying that correlation does not imply causation. Yeah, so this was the first talk on the first part of my talk, again, where I wanted to talk about the relationship of using causal inference methods to analyze teleconnections. Now in the second part, I'm going to move a bit away from causality here, but it's, let's say, still back of our minds. And in the second part, it's about so-called targeted weather regimes and how we can find them for using machine learning. This work is based on, this is done by Fiona Spuler. He was a PhD student I'm co-supervising together with Jenya Kovacic and Magdalena Balmaceda and Ted Shepard. And the paper is currently under review, but the preprint is available on arXiv, and it was also a short version of this was accepted for NeurIP's workshop on climate change last year. So you can also find this the poster there online. What we're interested here in so-called weather regimes, and so weather regimes, again, this link between statistics and physics is that so weather regimes are these recurrent patterns, so they are statistical representations of these recurrent and persistent atmospheric states. And you can think of them as maybe focus first on this figure on the right. These are the kind of canonical regimes for Europe. So this is, you're looking at the North Atlantic here. And if you, different ways to define weather regimes, but often you have these four typical representations of atmospheric circulation over the North Atlantic. AR stands for atmospheric ridge. Then the SB is this so-called Scandinavian blocking. You see this red blob over Scandinavia. And then you have the positive and the negative phase of the North Atlantic oscillation I already talked about. And you can think of, in a causal framework, maybe you can think of weather regimes as mediators between long-range teleconnections and local-scale impact variables. And this is what I try to visualize on this figure below. So on the left, you have different drivers. Could be ENSO, could be the polar vortex, which affect your weather regimes. But then again, weather regimes are useful because we know they have these links to weather situation or impact variables in different regions. And that's why weather regimes, let's say in the context of extended predictability, are so useful. And there are also many applications. For example, they're useful, or they have been shown to be useful for the energy sector, where weather regimes can give extended predictions of energy variables. In this case, or in Fiona's paper, we're interested in the application here is extreme precipitation over Morocco. Again, a region where we have poor regional climate information, especially on sub-season to seasonal timescales. But precipitation in Morocco is, of course, relevant. Actually, agriculture, it's rain-fed, and it employs up to 40% of the population. And there are also complex governance structures around water scarcity and flood management. The plot below shows winter mean precipitation in Morocco. This is based on error 5 data, sorry. On the left, you see the daily mean, and on the right, you see extreme precipitation, so the 95th percentile. The idea, or what the task here is, having so-called targeted weather regimes. So we want to find a weather regime, so these large-scale, these statistical representations of the large-scale circulation, but which are kind of optimized or targeted towards our impact variable, which is precipitation in Morocco here. And in this work, we compared 4 different methods to compute regimes. The first one is using principal component analysis in combination with k-means clustering. This is the state-of-the-art for how to compute weather regimes. This is widely used, but this is also a non-targeted version. So you just compute them to represent your circulation over the North Atlantic, regardless of the impact variable. And then we included 3 targeted methods, one being canonical correlation analysis, which uses the full field, and combine this also with k-means clustering to find whether these targeted weather regimes. The third method is one using based on variation autoencoder, combined with a regression task, which was based on a publication from neuroscience, and again, which we then combined with k-means clustering to come up with these regimes. And the fourth method is then one Fiona introduced, so-called regression mixture model variation autoencoder, RMMVAE, another acronym. And the important the first important difference here is that while the other 3 methods have this dimensionality reduction step and the clustering step in 2 different steps, actually this is done in one coherent statistical model in this RMMVAE architecture. Well, for the sake of time, I won't go into details here, but just to show these different graphical models in using plate notations, which based on these models, one can then quite easily, or I don't want to say easy, but you can then derive the joint probabilities for the loss function, which Fiona documents really nicely in this paper. So maybe just quickly look at the standard variation autoencoder on the very left. You have your inference model and the generative model. So you have some input data, in our case, Z500 data. You want to try to find a latent space, this latent representation, and then you have this generative model that you could reconstruct the data. And the middle part is this regression variation autoencoder. And the difference here is that you also have this T, which is learned. So for input data X, you not only learn the latent variable, but you also learn this targeted variable T, which is our precipitation index here, averaged over Morocco. And then finally, on the very right, this is this new architecture we introduced in this paper. This is RMMVAE, where you not only have learn the latent space, the latent variable Z, but you also learn this target scalar T, and you also learn the C. So she combines this with the regression, with the Gaussian mixture model, and you already learn. So you have probabilistic cluster assignment, which is represented here in this figure by the C component. I would skip to results here, and this is quite a busy plot, but you can just focus on the top columns. Oh, sorry, row. So the first panels here, you have the different weather regimes. If you use the state-of-the-art method of using PCA and k-means, so PCA for dimensionality reduction, k-means for the clustering, and below you have the associated precipitation over Morocco. And what you can see, for example, in the first regime, you have to see this blue blob, so negative geopotential height anomalies over Morocco and Iberia, associated with a lot of rain, not too surprising. If you go to the very right, you see a lot of red, so you have positive pressure anomalies over Europe and basically lack of rainfall. The other 3 methods we consider, they show well, somehow similar, but also different regimes and associated precipitation patterns. And the question, of course, which of these regime detection methods which are most useful for our task. So first of all, we can look at the organization of the latent space, which is kind of interesting. So what is shown here is a t-SNE plot. So the 10-dimensional latent space is further reduced to projected to a 2-dimensional space. And the first row, you see the 4 different methods. And the first on top, the green dots, they show the precipitation. So you see that, so darker plots show heavier precipitation. So you see these extreme precipitation events, they are organized differently for the different methods. Below, you see the assigned clusters, and you can already see some interesting things here. First of all, you can see that the latent spaces are definitely differently organized. This is maybe most obvious for the last 2 methods. So this regressional variation autoencoder, where basically you just have these aligned clusters. Whereas on the very right, our method, RMM-VAE, you have a more or differently organized latent space. So yeah, there are differences, and we then test 3 different ways what we think, let's say, a good targeted regime method should fulfill. The first one is, of course, that it's the goodness of the dimensionality reduction. So how good is our method in dimensionality reduction, and how good is it in reconstructing the original input data? This is the RMSE on the y-axis, and on the x-axis you have the 4 different methods. There are for the variation autoencoder methods, there are 2 versions, version 1 and version 2 for each. And the second, for the second version, the V2, we introduced another hyperparameter, which you can, where you can basically in the loss function, you can level down, let's say, the reconstruction error part. So you give more weight or more importance to the regression part. But we can first of all see that for PCA and CCA, so the first 2 box and whisker plots, there's a much larger reconstruction error, whereas for the VAE models, they can encode more information per number of dimensions than the linear methods, so the reconstruction loss is less. The middle method, so the regression variation autoencoder, performs slightly better, but for our method, so the 2 box and whisker plots on the very right, when we include even when we, let's say, put more weight to the regression task, it still performs quite well. So, and the nice thing is that we can make this trade-off between regression and reconstruction. So this V1 and V2, we can make this explicit here. Sorry, that is just said. So the second part is then on cluster persistence and separability. This is on the left, you see the persistence, and on the right, you see the silhouette score. So for separability, how well are the clusters separated? And yeah, I won't go too much into detail, but the important thing is on the left for persistence, you see that generally PCA and CCA, so those methods which performed worse in the first for the first metric, they're doing actually a good job. They are quite persistent. So is our method, but there's more spread. And when it comes to the separability, also PCA, so kind of the state of the art, shows a lot of separability, which in a way makes sense because it only has this one task of finding these regimes, and it doesn't have this additional task for the targeted or for the prediction of the impact variable. But again, you can see that our method, so the RMM-VAE, is kind of in the middle. So it shows high persistence, but more spread. But it also shows a higher silhouette score compared to the regression variation autoencoder. And then finally, we also look at information about the target variable. So how well are these regimes to how good are they really in encoding these information about extreme precipitation in Morocco? And we compare this for different cluster numbers. Sorry, I should have said this earlier as well. So K on the x-axis, you see different cluster numbers, and this is for tercites on the left, and for extreme precipitation on the right, and it shows the skill scores. So high values show high values are good here, high values are wanted. You see now that the regression version autoencoder, which didn't perform so well before, now actually leads with PCA and CCA being in last place, and our method again being kind of middle position and performing reasonably well. So the point here is that this targeted clustering, there is really what we show in this paper is that there is this trade-off between goodness of the dimensionality reduction as well as cluster persistence and robustness, and finally information of the target variable. So it's hard to, let's say, to excel in all these three categories, and for good reasons, because the different methods are designed for different ways. But I also want to highlight here that our method MVAE performs well in all these categories. It's not always first, but it is always, let's say, balances the three different tasks. It kind of balances out and finds a good performance in all three. So we do think this is kind of useful for weather regimes in general, and especially combining large-scale circulation again with impact variables. And of course, it's also not restricted to precipitation. I think I'm doing okay and okay with time, so I want to spend 5 more minutes on a slightly, well, not completely related topic, let's say, which is, with this trade-off I just mentioned in the context of weather regimes and the different task a different method has. And this is an example, another example of trade-offs in AI methods, and this is an example from Explainable AI. This is a paper led by Feline Bommer, another PhD student I'm supervising, together with Maria Höhne. And in this case, it's about using Explainable AI. Again, there's a nice talk by Amy McGovern on this topic in the seminar series. So Explainable AI, it's if you have a machine learning model, so this is the black box, or this first model, then there are different Explainable AI methods kind of to shine a light or to open this black box. So there's this second level too, where you have explanation, and there's a range of different methods such as gradient, LRP, etc. And in this paper, it's about evaluating these different explanation methods. So understanding what are the pros and cons of these different explanation methods to basically decide which one should use in the climate context. And the way we do this for evaluation, we have different metrics such as robustness, faithfulness, complexity, localization, randomization, and we have different ways to measure it and show how the different methods perform for a given task. In this case, or maybe I should say here, the task, if you look at the model, we have input data. This is based on a paper of Zach Leib and Libby Barnes, input data of temperature anomalies, and the model should predict the decade this temperature map comes from. So we have this labeled data, and the task is predicting the decade it came from. So one of these properties is, for example, robustness. So if you have input data, you have your network, you have your prediction of a decade, and again, you get your explanation with Explainable AI. So we have these local explanations. And a method on Explainable AI method is then called robust if you put some noise to the input image, and you can have slightly perturbed input images. If you then run through your network and you get your predictions, you want a robust prediction. What it means, you want your explanations to be fairly similar, so be robust to the noise given to the input data. That's what's meant by robustness. Just another example, faithfulness is if you have your explanation and you have, so it's the other way around, you start with the explanations, you can look which are the regions which are the pixels where you found, or grid points in this case, where you found a lot of relevance. If you mask these out, and if you mask those pixels out in your input image and run it through your network, then you of course wanted a faithful prediction a faithful explanation should give you a different prediction in this case, if you masked out the important regions. So in this paper, which is also on arXiv and it's revision now, we compare this for, in this case, for these two properties, but actually we compare this for all 5, and we can show how different state-of-the-art methods perform. And the message again being here that there's not a perfect method, but there's again a trade-off. And depending on what one wants and what one learns from the climate system, one should choose the method accordingly. Okay, so I come to my conclusions here in my summary. So again, I tried to kind of cover or try to show that I try my research. I'm interested in covering these aspects of climate science, causality with AI. And first, I tried to argue that to improve predictions, we really need this better understanding of the dynamical drivers of regional climate extremes. And this is, again, important for sub-season to seasonal context, decadal predictions, but also long-term climate projections. And I further argued that I think this requires really this causal reasoning and exploiting different data sources as well as methods. But what I also tried to show in the second part is that there's no such thing as a perfect objective method, even if we, let's say, try to go for objectivity in science. I think there's a lot of value in putting subjective expert knowledge in the analysis. And there's usually this trade-off, and I think we should be as transparent about it as possible. And then I didn't really have time to touch on this, but this intersection of AI and causality is exciting and really promising. And when I think of this, maybe it makes sense, or to me it makes sense. When it comes about drivers of regional weather extremes, we have all these different layers. So we start with gridded data. We try to extract features or regimes. We're interested in understanding these mechanisms, how different large-scale patterns and regional modulators, how they interact to basically come up with this information. And I think this is kind of my general outlook, that AI can and also will help with all of these tasks. But how to combine them, I think this is, excited research ahead of us. So I hope I was doing okay time-wise. So thank you for your attention and looking forward to your questions.
Brilliant, thank you. No, perfectly on time. Very good. Very interesting. Just for people listening, if you're in the chat, you can also just post your questions in the chat at any time, and we'll try to pick them up from here. But I might just kick us off with one. Very interesting, in particular, also the sort of regime-based analysis where you don't have to do the dimensionality reduction step before. And I guess there could be quite a wide range of sort of causal attribution applications for that, because that is typically many of these methods work so well once you have a dimension reduction step already done. So a question I have is sort of maybe a broad one is, this approach, do you think it also generalizes to so whether regimes are really well defined, and you find them with many methods, and you see also in your work that broadly you find similar regimes, but your approach obviously is not so dependent on your exact regime definition to start with, because you just put your data in. Do you think it also generalizes to smaller scales and other weather regimes that we wouldn't normally find so easily, or other regimes you want to tackle for causal investigations?
I'm not sure if I understood the question completely. So I think, or let's put it differently. I think a lot of when it comes to clustering and regime detection, I think there's a lot of discussion as are there 4 regimes, are there 5 or 6 or 7? And I don't think this is maybe well, it's a valid question, obviously, but maybe that's not the most important question. So I really think, personally, I find it more exciting about this question of what the regimes can do, what they cannot do. And I think if our interest is in having really using regimes for example, extended predictability, and we're interested in a certain impact variable, such as precipitation, but it could also be, energy shortfall, then using AI and using, let's say, all these tools to kind of optimize our latent space, I think this is exciting. And of course, we also tested, I often showed, I think 5 regimes, because we have to make some choice. But think it shows the reasoning of subjectivity, bringing subjectivity that is okay, and it will depend on user values, how much they want. But again, I'm not sure if I covered your question.
No, it was a very good answer. It was slightly sort of. I mean, I was thinking a little bit if you don't take geopotential height or something where you have these sort of broad, large-scale features, but often we might be interested in features that are much smaller, and you could just feed it raw precipitation data, which is very granular and wouldn't normally in many traditional methods, you would find it much harder to define your regimes. So I wondered if there's applications for this.
Yeah, I'd say yes, but then of course one has to show it. So I leave it yes. Let's see. This would be my diplomatic answer.
Perfect. There's a question in the chat actually from Julian Smith, and asks, what teleconnections mechanism have you found with the snow cover regime in Eurasia, and what physical explanation do you have if such studies were done? Thank you. Actually, Julian was actually the one who transferred the one into the chat, so there was my error. The question was from Maxime.
Yeah, thanks, Maxime, for the question. Well, I guess snow cover, there are of course different documented feedback. So this was not particularly, let's say, related to one study. So there's I don't know, the snow monsoon mechanisms, but in this case, and I guess he covered Eurasia, and this was referring to, for example, work from Judah Cohen on how Siberian snow cover leads to a weakening of the polar vortex via so the chain is, you have more snow cover, you have more Ural or Siberian increase in Siberian high pressure anomalies, which then interferes with climatological waves, leading to weakening of the polar vortex. That's, let's say, one of the popular hypotheses when it comes to snow cover or Arctic mid-latitude linkages. But to be honest, let's say in this very schematic figure, I really use snow cover as kind of one of the slowly moving boundary condition in the climate system, which might give us some window of opportunity for sub-seasonal predictions.
Great.
I have a brief question, if that's okay, Philip. I really like this framing, Marlene, where you kind of make explicit these trade-offs that are sometimes implicit in these choices that we make of the tools we select, and being able to quantify those trade-offs is really powerful, because then you can design algorithms that optimally target the ones that you feel are most important for a given task. One of the things that occurs to me, and one of the things I've struggled with a little bit when using some of these causality tools is, obviously they, by construction, try and minimize complexity. They try and make it really sparse and maximally kind of informative, I guess. But I found that they sometimes are not then as robust. So if you give it slightly different data or slightly different hyperparameters, you get a slightly different graph. And I found that difficult to kind of move forward then and kind of trust, I guess, the algorithm. Can you speak to approaches that are, that we can use in, the explainability bit that you said, but applied to the causality tools?
Yeah, thanks. That's a big question. So, I guess, let's say, when it comes to lack of robustness, I think that's what people, or including myself, also experienced when it came to causal discovery. So which I didn't really cover here, but it's like when you have your input data, different time series, let's say, and you go high dimensional, then you change a bit of your input parameters, and then where the graph looks different every time, basically. Agreed. So let's say in this weather regime example, let's say we made our life easy because, and we didn't really show, but the underlying causal graph is you have Z500 leads to precipitation, which I think we can agree on. But the next step is, as you said, is then of course including more information and more causal drivers and teleconnection, and then we open the field of causal representation learning. Well, let's say I trust Fiona Spuler to and let's say she's interested in working on this. So I do think we will get there. So I don't think let's say the current state of research is where we have to end. But I agree that there is really a spectrum between interpretability and data-drivenness. I don't know if this makes sense, which applies to all methods, including causality. And of course, let's say these very nice little diagrams, which I personally like, where you have three drivers, you have your ENSO and your JET and California precipitation. This is where everybody can agree on, but of course we want to do more. But I do think we have to find this balance, and that's why I think making these trade-offs explicit is so relevant. So I don't have a precise answer. I just think again it depends on context, and if you have a large CVET ensemble of different models, you probably want to be small scale in the sense of having fewer variables, whereas if I don't want to explore things in just one model, you can maybe go a bit wider and include more things. So, but yeah, I think fully user and context dependent.
Thank you.
Great. So there's a question in the chat that always comes up when it comes to clustering. How did you determine the optimal number of clusters in your web regimes?
So thanks for the question. So we didn't. We basically acknowledged that there is different discussions around it. So what we did was, let's say we looked, of course, at these typical within cluster variability metrics and so on, and that's why we decided that 5 was a reasonable good number, which we used then for several plots in the paper. But for most of the metrics, we actually showed the skill, the performance for different cluster numbers. And sometimes you see an increase, or you see let's say a shift, switch for different methods when you have more numbers of clusters, what we also try to interpret. But there was, let's say, more or less the results were qualitatively robust. So we again left this to a potential user.
Second, I lost you for 1 second. Okay, it's back. No, that's great. Maybe a slightly related follow-up question to the question I asked before. So I was curious a little bit, and that is, I'm not sure there's an easy answer to that question, but it's still relevant. Thinking a little bit about ethical considerations. And I'm thinking, so the choice of input to some of these models and the regime classification will determine a lot sort of which regimes we find. But I think if you give it surface pressure, you will always emphasize the mid-latitudes and not the global south. So wonder if some of these methods could generalize to multimodal data, where you can maybe bring in other data sets and we avoid certain biases. I mean, it's coincidental, obviously, that the mid-latitudes are not the global south. But would an inclusion of sort of multimodal data and multimodal regime classification help to address some of this?
So let's say, first of all, I share the concern of this general problem. I don't think it particularly applies to this case here, because we pre-select the region. So basically, let's say the bias was in saying we care for Morocco in this case.
Yeah, I mean more in general, yeah.
Yeah, so, and there's so much literature on regimes, particularly in the North Atlantic. So this was an attempt to, let's say, shift a little bit south, at least, to a region where there's way less literature on. So that was one of the reasons why we looked at Morocco and Mediterranean regimes and not the classical North Atlantic ones. I guess maybe it comes back to Duncan's last question about maybe also robustness, but I feel like when it comes to using machine learning on the seasonal ranges, I feel like that maybe these kind of global solutions that we have in AI-driven weather forecasting, that those will become more difficult. And I personally think it's exciting to bring in this knowledge of teleconnection for when it comes to these regional aspects. I feel like this is maybe the way to go, because we have these windows of opportunity, but often there's really this lack of predictability. So multi-model, probably yes, because there will be biases also in the data. But let's say generalize in a global sense, I would be more hesitant, let's say.
Enough. Thank you very much. Very, very clear answer. I think there's a last question in the chat which we can maybe take, and that's more, I think, useful for many people to think about learning more about causal methods. is Julia Pearl's work still the right place to start, or where would you guide people to start if they want to pick this up?
Well, I think so, yes. And I think, well, maybe start with our paper if you're interested in the climate science context. But yeah, well, I don't know. I think well, it's a silly answer, but the internet is just great. There's so many great resources. And again, I think it depends on which language you are trained in. So we wrote this paper because I think it speaks, I hope it speaks the language of climate scientists or people with a background, let's say, in large-scale dynamics or teleconnections. But obviously, if you have a machine learning background, you will have a different, you speak a different language, let's say, and you need different aspects of it. Actually, it's also quite, interesting, but also a bit entertaining if you on Twitter or X, you can really see these discussions. Julia Pearl has, for example, with Jan Lecon from NYU, I think, and Facebook, right? So there are really these heated debates online from these top scientists and winners of Turing Award, whether AI is really, can we have real AI without causality? Is causality needed? So, so maybe just follow those discussions. And then, but yeah, there are so many great resources, and I'm happy to share some links which I found helpful. But I think it will depend a lot on your background and your training, what kind of the access one needs.
Brilliant. I think that's a fantastic way to end it. Good guidance. Thank you a lot, Marlene, for a really excellent talk. We can obviously go back to this online later on and reread all the references. For those of you interested, next week we're actually back again. There will be a talk by Paolo Ceppi and Per Novak. It will be mostly about cloud feedbacks and machine learning approaches to tackle these. So also very relevant questions. So come back.
Yeah, great.
Great.
And they also applied causal discovery.
I think it'll come up, yeah.
Exactly. So there's a thread emerging. Perfect. Thank you very much for joining.
Thanks so much.
Bye, everyone.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.